Okay, so in the last video we talked about refraction and we talked about Snell's Law and we did some examples with Snell's Law. So today we're going to do a few more examples with refraction and Snell's Law, and then we'll talk about the last thing having to do with refraction and Snell's Law, which is called total internal reflection. Okay, and so take a look at example 3. Okay, this is from the IB exam from a couple years ago. It's a multiple choice question. And it says a light ray passes from air to water as shown. What are the change in the wavelength of the light wave and the change in the angle the ray makes with the normal to the surface? Okay, so try to answer that question on your own. Okay, so whenever you see a wave going from one medium to another, the first thing that should pop into your mind is refraction. Okay, now in this case, it's a light ray, or it's a light wave. It's an electromagnetic wave. And remember, when you're talking about rays, that's just one way to visualize a wave. Okay, so during refraction, remember that the frequency remains constant during refraction, and so the frequency of this light ray in the air and the frequency in the water are going to be the same. Okay, what does change is that the wave speed and the wavelength both change, which is really what causes the wave to bend. Okay, so that's kind of how refraction works. But because the frequency is fixed, that means the quantity F equals V over lambda, which just comes from rearranging the wave equation, that has to be a fixed quantity. Okay, that means that if V increases, lambda also has to increase by the same proportional amount in order for the ratio to be the same. Okay, so with that in mind, let's see if we can answer this question. Now, the refractive index in air is taken to be 1. That's not something that would be given to you. That's just a fact that you need to know. And the refractive index in water, it doesn't really matter what it is, but it's going to be more than 1. Okay, water has what's called a higher optical density than air, and so the refractive index is going to be higher than 1 in water, which means that basically when light travels into water, it's going to slow down. Okay, the actual value is probably like 1.33 or something like that, but it doesn't really matter as long as you know it's more than 1. Okay, now if you know that water has a higher refractive index than air, which air and a vacuum both have a refractive index of 1, essentially. Air is actually like 1.00 something. A vacuum has a refractive index of 1. You cannot have a refractive index lower than 1. Okay, and so that means that when the light ray goes into the water, it's going to slow down. And so if V decreases, that means the wavelength also has to decrease in order for this ratio to be the same. All right, that eliminates answer choices A and B. Now, what's going to happen with the angle that the ray makes with the normal? Okay, so remember the normal is the imaginary perpendicular line that's perpendicular to the boundary between the two media. And also remember that when you're going from a lower to a higher refractive index, the ray is going to bend towards the normal. Okay, we talked about that in the last video. So that means the angle with the normal is going to decrease. Okay, so that means the wavelength is going to decrease and also the angle is going to decrease. And an easy way to remember that is just to think whichever side, whichever medium has a higher refractive index, the angle should be smaller on that side. All right, so hopefully you got example 3. Okay, pause there if you need to look at this more, then we'll do one more example. Okay, so one more quick example. Here we have a diver working underwater, and a ray of light from his lamp strikes the surface at an angle of 55 degrees to the horizontal. The picture is shown here so you can see exactly what that angle is. Take the refractive index of the water as being 1.33. Read the question carefully and make sure you answer the question being asked. At what angle to the horizontal will the ray travel after it leaves the water? Okay, read the picture carefully and read the question carefully and see if you can figure that out. Okay, so let's take a look at how you would approach this question. Okay, so the first thing you need to realize is that the angle that you're given is not the angle measured with respect to the normal. Okay, remember you always have to measure angles with respect to the normal. And so this 55 degrees is not with respect to the normal. You have to find the complementary angle, which is actually 35 degrees. Okay, so I'm using Snell's law to do this calculation. I have n1 sine theta 1 equals n2 sine theta 2. n1, because it's starting in the water, which has a refractive index of 1.33, I do 1.33 times sine of 35 degrees, and that's equal to n2, the refractive index of air is 1, times sine theta 2. Okay, so theta 2 is going to be the inverse sine of 1.33 times sine of 35 degrees divided by 1. Please make sure your calculator is in degree mode when you do that calculation. Okay, so 1.33 sine 35, and I get 49.7 degrees, which is about 50 degrees. Now, is that the answer to the question? Well, let's see what the question says. It says at what angle to the horizontal will the ray travel after it leaves water? Again, remember, anytime you are doing a problem with Snell's law, you always measure angles with respect to the normal. Okay, so what's going to happen is that 50 degrees we just found, that is going to be right here measured from the normal. The question is about the angle to the horizontal, which is this complementary angle down here. Okay, if that's 50 degrees, then this angle right here should be 40 degrees, and so that is the answer to the question. Okay, so pause it there if you need to look at that some more. Snell's law problems are not really complicated as long as you're in degree mode, and as long as you make sure that you understand that the angles always have to be measured from the normal. Okay, so this is just a picture showing you what that would look like. Alright, so the last part of this section is about what's called total internal reflection. So back when we did example 2 in the last video, the last part of example 2 says, how would your answer to the first question be different if the angle of incidence was 50 degrees? And if you did the calculation correctly and you plugged in 50 degrees here, your calculator should have blown up with an error message. Okay, and so just to refresh your memory, that the optical fiber has a refractive index of 1.44. If the beam of light is trying to go from the fiber into the air at an angle of 50 degrees, that's actually not physically possible. And I'll kind of show you what that looks like on a simulation. Okay, so here we have a simulation. I basically am going to try to adjust the angle so it's at about 50 degrees, which is, I believe, over here. And notice we actually don't have any refraction at all. Okay, all we have is reflection. Okay, now why does that happen? Well, if I decrease the angle enough, then I do get refraction, right? If I decrease the angle of incidence. Okay, but watch what happens as I slowly increase the angle of incidence. This refracted ray is going to get closer to the boundary line faster than the reflected ray over here. Okay, and so what's going to happen is at some point it actually hits the boundary line, and then I don't have any more refraction. And so this is called total internal reflection, not refraction, reflection, because the light is basically stuck in the fiber. Okay, there's light in the fiber, but it's hitting the boundary and it reflects at the boundary rather than refracts. Okay, so this is called total internal reflection. All right, so make sure you add this to your notes. Okay, there's lots of interesting applications of total internal reflection, and we'll watch some application videos here in a minute. One of the key applications has to do with fiber optics, fiber cables. If you ever have like Frontier, Fios, or I guess Google also has fiber optic internet services that they provide. Basically, the way that works is they send signals using light rather than electrical signals, and so they get really thin pieces of fiber and they shoot light in one end, and because of the way the material in the fiber cable works, basically the light, rather than escaping the cable, it actually reflects all around the cable, and it's able to keep bouncing, and come out the other end without any light escaping. Okay, and so that is one really classic application of total internal reflection. In one of the videos we'll see here in a minute, they talk about that in the video. Okay, now, what do you need to know about total internal reflection? Well, first of all, you can only get total internal reflection if you're starting off in a medium with a higher refractive index and going into a medium with a lower refractive index. Okay, so back to the example we did, going from air to fiber, you would never ever get total internal reflection. You can only get it when you're going from a higher to a lower refractive index. All right, now, if you go look at the simulation, what you should see is that the angle of incidence, if the angle of incidence is low enough, then we do get refraction. Okay. However, if we increase the angle of incidence at some angle, right, I'm having some issues with my mouse, but right about here, we get total internal reflection. And then if we keep increasing the angle of incidence past that angle, then we just still have total internal reflection. And so write this down. This is a definition. Definitions are important. The minimum angle for which total internal reflection occurs is called the critical angle. Okay, so theta c, that's called the critical angle. How do you calculate the critical angle? So basically, if you think in terms of Snell's law, you have n1 sine theta 1 equals n2 sine theta 2. What happens when you're going from a higher to a lower refractive index is as you increase theta 1, theta 2 also increases. Okay, but the highest value that theta 2 can ever have is 90 degrees. Okay, it can't go past 90 degrees because that would just be reflection, like normal reflection. Okay, so basically theta 2, the maximum value that theta 2 can have is going to be 90 degrees. Okay, so with that in mind, we can calculate theta 1, or what value of theta 1 would give us theta 2 is 90 degrees. Now again, the critical angle is the minimum angle of incidence that total internal reflection occurs. Any angle greater than that, you also get total internal reflection. All right, so we can derive an expression for that. So let's say we have n1 sine theta c. So when the angle of incidence, theta 1, is equal to the critical angle, then what happens by definition is that theta 2 becomes 90 degrees. Now sine of 90 degrees is 1, and so that means that if this is 1, it basically doesn't matter. So we have sine theta c equals n2 over n1, and so theta c, the critical angle, is the inverse sine of n2 divided by n1. Okay, and so that is an expression that lets you calculate the critical angle. Keeping in mind, number one, that this equation is not given to you. You would be expected to know where that comes from and be able to reproduce that on your own because it's not a given equation. If you understand the concepts involved, then it's not hard to figure that out, though. Also keep in mind that this equation only gives you a valid answer as long as n2 is less than n1. Okay, because the domain for inverse sine only goes up to 1, and if you try to plug in a number greater than 1 into inverse sine, then your calculator is going to blow up. Okay, and that's because you can only get total internal reflection going from a higher to a lower refractive index. Okay, so pause there, make sure you add that to your notes. And let's just do a few quick examples. Okay, so example 0.5, this is just like a cool visual demonstration of total internal reflection happening. There's a laser pointer, and it's shining a light into this tube, and basically what happens is the light gets into this plastic tube, and then because the angle of incidence here at this interface is greater than the critical angle, when it tries to go back out into the air, it gets trapped, and so you can see it reflecting around in the glass there. Alright, so what is this phenomenon called? Obviously total internal reflection. What conditions must be met in order for this phenomenon to occur? Well, theta 1, the angle of incidence, has to be greater than or equal to the critical angle, and plus it only works if n1 is greater than n2. That means the refractive index of the medium that you're in has to be higher than the refractive index of the medium you're trying to go into. Alright, so let's watch some application videos, and then in class we can do some more examples as far as doing calculations. Hey, I really want you to check out these videos. I'm going to link all of these videos in. I've kind of put them in order that I want you to watch them in. Some of these are just like cool, like, helping to understand the concept, and some of them are really, really cool applications, especially the grapes in the microwave one. That's a really awesome video. Okay, so I am going to link all of these videos in now, and I'll get your thoughts about these videos here in a minute. Okay, so before I end the video, I just want you to try to get an answer to example 1 on your own. Alright, so as always, please let me know if you have any questions, and I'll see you guys in the next video.